Swayam Prabha. Digital India. Educated India.
Namaskar. So, in the last class we were discussing about the series RLC circuit and its response when the source is not available. So, we will continue our journey from there in this week also, and let us see when you apply step input, then what will happen. So, let us first understand what we discussed in the last class. We discussed about the source free series RLC circuit, and when we were discussing, we mentioned that the characteristic equation which we have we get from Kirchhoff voltage law is of second order in nature. That is why it is called a second order circuit. Now, if you see this figure, the energy is initially stored in inductor as well as capacitor. So, capacitor is initially charged with voltage V naught and inductor is having some initial current as I naught. So, since these two elements are storing the energy, that is why the circuit is having some current flowing. Now, we stabilize that the equation using KVL we will get is second order equation, that is d2I by dt2 plus R by L into di by dt plus I by LC equal to 0. Now, we assumed that the current is A equal to A into e to the power sigma t. Now, if you put the value in the above equation and we solve it, we found that there are two roots possible for the equation, and we saw that sigma 1 and sigma 2, and we assumed that let us say alpha is r by 2l and omega naught is equal to 1 by under root LC, and when we simplified we got sigma 1 and sigma 2 as minus alpha plus under root alpha square minus omega naught square, and sigma 2 is nothing but minus alpha minus under root of alpha square minus omega naught square. Now, based on the values of sigma 1 and sigma 2, we found that there are three types of solutions available for the equation. That is, first case, when sigma is when alpha is greater than omega naught, it means that the circuit has overdamped case. When alpha is equal to 0 or alpha is equal to omega naught, we have critically damped case. When alpha less than omega naught, we have underdamped case. Now, when we say that it is overdamped and alpha is greater than omega naught, the condition which we got was C greater than 4L by R square. Now, based on that condition, the current value what we found was A1 into e to the power sigma 1 t plus A2 into e to the power sigma 2 t. Now, if you plot the curve, that is the variation of current I with respect to time, we saw that the curve will look like this, which will start from 0 and eventually it will settle down at some point, or because it is a source free, then it will come back to 0 at as time t tends to infinity. Now, second case what we discussed was alpha is equal to omega naught, where the condition is that C is equal to 4L by R square, and we found that current in that case is I at time t is equal to 0, at time t is A1 t plus A2 into e to the power minus alpha t, and when we plot this the value of current I with respect to time t, we saw that the characteristic of the current is as shown in the figure, and we saw that at time t is equal to 1 by alpha, the current will be at its maximum value. Now, the third case what we discussed was alpha less than omega naught. In that case, C was less than 4L by R square, and we saw the current equation which we got was having exponential term as well as sine and cosine terms. So, when we plot the variation of current I with respect to time, we saw that it was exponentially decaying as well as it was oscillatory, that is because of the sinusoidal components available, and the time period was 2 pi by omega d, and it was exponentially decaying because of the exponential component available. So, this is what we discussed in the last class. Now, let us see what are the various properties of series RLC network. Now, we can say that damping effect is due to the presence of resistance R, because the damping factor alpha depends upon resistance R. So, we can tune the value of R on and get the various kind of damping effects. When the condition is alpha is equal to 0, means R is equal to 0, it means that we have a pure LC circuit, and in that case we will have only omega naught, that is 1 by root LC, because alpha is 0. So, then this is nothing but your undamped natural frequency. So, what will happen in that case, that response is only oscillatory, and then circuit is said to be lossless, and because of no dissipating component, the energy will be keep on oscillating. Now, by adjusting the value of R, the response may be made undamped, overdamped, or critically damped, or maybe underdamped. So, the R is the important component in the series RLC circuit. Oscillatory response is possible due to the presence of two types of storage element. So, here we have inductor as well as capacitor, which act as a storage elements. So, having both L and C allow the flow of energy back and forth, because of that we get the oscillatory response. Now, the damped oscillation shown by the underdamped response of the circuit is also known as ringing. Now, the critically damped case is the borderline between underdamped and overdamped cases and decays the fastest. So, if you have a system which is critically damped, it means that it will decay the fastest. With the same initial conditions, the overdamped case has the longest settling time, because it takes the longest time to dissipate the initially stored energy in the storage elements. Now, if we want the fastest response without oscillation or ringing, what we need to do? We have to make the system critically damped circuit. So, in that case we will get the fastest response without any oscillations. Now, let us talk about the source free parallel RLC circuit. So, what will happen in this case? You will have R, L and C, all these components in parallel. So, what you need to do? You have to first figure out what is the initial condition. So, let us assume that initial current flowing through the inductor is I naught and initial capacitor voltage is V naught. So, what you can write, I at time t is equal to 0 is nothing but I naught, and you can represent it like the integration of V at time t into dt, where integration ranges between minus infinity to 0, because this is the time where the system is at rest initially. So, what is the current flowing at time t is equal to 0 will continue to flow in the circuit at time before t equal to 0. Similarly, for time t is equal to 0, we are assuming that capacitor is initially charged with voltage V naught. Now, what will happen? If you assume these two initial conditions and the circuit is in parallel, then the best thing is that you can apply Kirchhoff current law at the node where all the 3 elements are connected. So, now what will happen? You will say that sum of the resistor, inductor and capacitor currents will be 0 at this node. So, you can write the current which is flowing through resistor is V by R. Let us assume that the voltage at this node is V. So, the current which is flowing through resistor would be V by R. Similarly, current flowing through inductor would be 1 by L 0 to t V t dt, and the current flowing through the capacitor will be C dV by dt. So, the summation of all those 3 elements would be 0 at that node. Now, what you need to do? The equation we have just got because of the application of KCL, let us differentiate the equation once again. So, what we will get? We will get d2v by dt2 plus 1 by RC dV by dt. So, basically the value of the component C, you can take them in denominator. So, it will become dV by dt into 1 by RC plus 1 by LC into V equal to 0. Now, we can obtain the characteristic equation by replacing the first derivative by sigma and the second derivative by sigma square. So, if you put the value of sigma and sigma square in this equation, what you will get? You will get sigma square plus 1 by RC into sigma plus 1 by LC equal to 0. So, since it is a second order equation, you will get 2 roots of this particular characteristic equation. What would be the roots? The roots would be sigma 1 and sigma 2. Let us assume the values are the characteristic equations roots are sigma 1 and sigma 2. The value of sigma 1 and sigma 2 can be given as minus 1 by 2 RC plus minus under root of 1 upon 2 RC square minus 1 upon LC. So, if you see this equation, for sigma 1 you can place the plus sign, and for sigma 2 you will use negative sign. So, you will get simply 2 roots. Now, let us assume that the 1 upon 2 RC is nothing but alpha and 1 by LC is nothing but omega naught square. So, if you put these values, the sigma 1 2 which are the roots of the characteristic equations can be represented as minus alpha plus minus root of alpha square minus omega naught square. Now, if you see these roots, these are similar to what we got when we were analyzing the series RLC circuit. So, what will happen that you have assumed alpha and omega naught, and based on that you can again have the 3 possible solutions. So, if you compare similar to your series RLC circuit, in this case also you will get 3 possible solutions. The conditions for these possible solutions would be: one condition is alpha greater than omega naught, second is alpha equal to omega naught, and third is alpha less than omega naught. Now, when alpha is greater than omega naught, you call it as overdamped case. So, what will happen if you put the condition, if you replace alpha and omega naught values with this with these value which you assumed previously, you will get the condition that when L is greater than 4 R square C, the circuit will be overdamped. Now, in that case the roots of the characteristic equations are real and negative. This is similar to what we got in case of series RLC circuit also. So, similarly, the response which you will get in this case will again be A1 e to the power sigma 1 t plus A2 e to the power sigma 2 t. So, this response would be similar to what we got in case of series RLC circuit. Now, in case of critically damped case where alpha equal to omega naught, your condition will be the system will be critically damped when L equal to 4 R square C. So, in that case also the roots are real and equal. So, you can say the response would be V t is equal to A 1 plus A 2 t e to the power minus alpha t. So, this is again similar to what we got in case of series RLC circuit. Now, the third case is underdamped case when alpha is less than omega naught, that means the value of L is less than 4 R square C. So, in this case the roots would be complex and can be expressed as sigma 1 2 is nothing but minus alpha plus minus j omega d, where omega d is root of omega naught square minus alpha square. So, you can compare both of the cases like series RLC and parallel RLC circuits, you will come to know that the roots are same, the only change would be the condition, because here the elements are in parallel. So, that is why the case wise condition where L is related to R and C would be different in both of the cases, but finally the response would be similar to what we got in case of series RLC circuit. So, in this case also V t would be equal to e to the power minus alpha t, which will give you the exponentially decaying response plus A 1 cos omega d t plus A 2 sin omega d t. So, if you plot voltage V with respect to time t, you will get the oscillatory response and it would be decaying. So, in both of the cases, like in case of series RLC circuit, we were comparing the current I with respect to time. In this case, since it is a parallel RLC circuit, we are interested in finding out the voltage with respect to time. So, here you will again get the oscillatory response with exponentially decaying. So, exponentially decaying because of this term, oscillatory response would be because of this term. Now, let us talk about the case when we apply an step input to a series RLC circuit. So, earlier when we discussed, we discussed the source free response of series RLC circuit. Now, what we are doing here, we are connecting the source with one switch which is closed at time t is equal to 0. So, when you connect the switch, there would be a current flowing in the mesh, let us say this is I. Now, what you need to do, you have to write the mesh equation for this circuit. What we can assume? We can assume initially the voltage across capacitor, let us say it is V naught, and current which is flowing through inductor can be considered as I naught. So, these two would be the initial conditions which we know, and based on that we will try to simplify the loop or mesh equation which we get from the KVL. So, when you apply KVL at time t greater than 0, the moment when you close the switch, you will get L di by dt plus R I plus V, which is voltage across capacitor, equal to external voltage source V s. Now, you know that I is nothing but C dV by dt. So, you can put the value. So, what you will get? You will get the equation in second order. So, what you will get? You will get d2V by dt2 plus R by L, you can take L in the denominator, plus V divided by L C equal to V s by L C. So, this is what you get when you put the value in the equation. Now, when you compile the characteristic equation will not be affected by the presence of DC source. So, what you can do, you can see the solution of this equation can be divided into two parts, means it will have two components, one is natural response and other is forced response. So, this will be similar to what we discussed in case of series RL or series RC circuits, in case when we apply the step input to those circuits. So, similarly here also we can divide the total response of the circuit in two parts, one is natural response and other is forced response. Now, you can see that the total response will be can be written as the forced response, that is VFT, plus natural response, that is VNT. Now, to find the natural response, what you need to do, you have to set the value Vs equal to 0. So, when you put the value Vs equal to 0 in this equation, so you will get only the left side component and this would be equal to 0, and this is same equation which we get when we analyze the series RLC circuit without any external source. So, based on the previous discussion, in case of source free series RLC circuit, we can write simply the natural response of the circuit, and we can also say that there are three conditions which are underdamped, overdamped and critically damped cases. In case of overdamped, what we can write, Vt is nothing but A1 e to the power sigma 1 t plus A2 e to the power sigma 2 t. Similarly, in case of critically damped, you can write Vt is nothing but A1 plus A2 t into e to the power alpha t, alpha is your damping coefficient, and in case of underdamped case, the value of voltage at time t would be e to the power minus alpha t into A1 cos omega dt plus A2 sin omega dt. So, these three equations are same equations which we got when we were analyzing the series RLC circuit without any external source applied. Now, to find the forced response, you need to find out what would be the steady state or final value of voltage t. So, that is Vt means the time which tends to infinity. The final value of capacitor voltage will be the same voltage, that is the source voltage. If you see the figure, when you keep on this particular switch on for very long period, what will happen? In that case, your inductor will act as a short circuit. So, the total voltage would be applied across the capacitor will be equal to the source voltage, because after the capacitor is charged to its full value, your current I will also be 0. So, you will get finally the capacitor voltage equal to Vs. So, the same value we will use and we will say that the forced response is nothing but the source voltage. So, this we have got. So, what we can write now, the complete solution for the overdamped, underdamped and critically damped cases can be written as Vt. So, in case of overdamped, you will say that it is Vs plus A1 e to the power sigma 1 t plus A2 e to the power sigma 2 t. In case of critically damped, you have to just write Vs plus A1 plus A2 t into e to the power minus alpha t. For underdamped case, you will write Vs plus e to the power minus alpha t into A1 cos omega dt plus A2 sin omega dt. So, this would be in case of underdamped case. Now, what is left is the value of parameters A1 and A2. So, these values we can calculate with the help of initial conditions, which we assume that at time t is equal to 0, we have voltage V naught and current which is flowing through inductor is I naught. So, we can use that value and find out the value of those constants which are unknown in these 3 equations. So, with this we can close our today's session, where we discussed about the step response of a series RLC circuit. So, we will continue our discussion in the next class, where we will discuss about the step response in case of parallel RLC circuit. Thank you.